Look up at the night sky, and for a moment, let yourself get lost in its vastness. Those countless pinpricks of light are more than just stars. They're ancient storytellers, whispering secrets of a universe far stranger than we often realize. Among these cosmic mysteries, few are as enigmatic as globular clusters, tightly packed cities of stars, some nearly as old as the universe itself, where gravity pulls hundreds of thousands of suns into glittering, swirling spheres. These clusters are like celestial time capsules, preserving clues to the universe's wildest chapters, from cannibalistic stars to rogue black holes lurking in their cores. Imagine a place where stars are crammed so close together that their combined light creates an eerie, perpetual twilight. A place where planets, if they exist, would see not one sun in their sky but hundreds, each blazing just a few light years apart. Globular clusters defy everything we expect from the cosmos. They're relics of a younger, more chaotic universe, and within their ancient embrace, they hide anomalies that challenge our understanding of physics itself. Some stars here move at impossible speeds, others glow with elements that shouldn't exist, and a few might even be stolen from long-dead galaxies, swallowed whole as these clusters drifted through the cosmos. Tonight, we're diving deep into 30 of the most astonishing discoveries hidden within these starry behemoths, each one stranger than the last, from stars caught in a cosmic tug of war to the eerie possibility of advanced civilizations hiding among their crowded suns. Globular clusters are more than just beautiful oddities. They're portals to a universe that doesn't play by the rules. So buckle up, we're about to unravel mysteries that will leave you questioning everything you thought you knew about the night sky. One of the most baffling mysteries hiding within globular clusters involves stars that simply shouldn't exist, stellar rebels that look far too young for their ancient surroundings. Picture this, an entire city of stars, all born around the same time over 10 billion years ago, yet a handful shine with the vibrant blue hue of youthful energy, standing out like teenagers at a retirement home. These cosmic anomalies, known as blue stragglers, defy every rule we know about how stars age. So how do stars in these ancient clusters stay so inexplicably young? The leading theory suggests violent stellar collisions and cosmic theft on an unimaginable scale. In the densely packed cores of globular clusters, stars don't have much personal space. They brush past each other at dizzying speeds, sometimes getting so close that gravity yanks them together in a violent merger. When two older stars crash and combine, their mixed fuel reignites nuclear fusion, creating a hotter, brighter star that masquerades as a newborn. Other blue stragglers might be stellar vampires, siphoning material from a nearby companion star until they've stolen enough gas to rejuvenate themselves. But the strangest part, some of these stars aren't just breaking the rules, they're rewriting them. Their chemical compositions reveal elements that shouldn't exist in such ancient environments, hinting at exotic processes we're only beginning to understand. It's as if the universe left us a series of cosmic breadcrumbs, each one leading to more questions than answers. What else could be lurking in these dense stellar cities, bending the laws of physics right before our eyes? Globular clusters have long been thought of as simple, predictable systems, dense balls of stars bound together by gravity with little else to complicate the picture. But recently, astronomers stumbled upon something that shattered that assumption: the eerie gravitational fingerprints of dark matter. For decades, scientists believed these clusters were nearly devoid of dark matter, their gravity dominated entirely by the sheer number of visible stars packed into such a tight space. That's why the discovery of strange gravitational anomalies within some clusters sent shockwaves through the astrophysics community. Take the cluster NGC 5139, for example. Measurements of how its stars move revealed something bizarre. Their velocities didn't match predictions based on visible mass alone. Some stars whizzed around at speeds that should have sent them flying out of the cluster, yet they remained stubbornly in place. The only plausible explanation, an unseen gravitational force at work, a hidden halo of dark matter woven into the cluster like an invisible scaffold. This revelation sparked fierce debate. If dark matter really is lurking in these ancient star cities, it challenges our entire understanding of how they formed. Were globular clusters born inside massive dark matter clouds, or did they capture this mysterious substance later in their lives? Some researchers argue that what we're seeing isn't dark matter at all, but rather the gravitational echoes of black holes or leftover debris from violent stellar collisions. Yet increasingly sensitive observations keep pointing back to dark matter as the most likely culprit. What makes this discovery even more unsettling is how selective it seems. Not every cluster shows these gravitational anomalies, meaning dark matter's role might vary wildly from one to another. Could this mean that some globular clusters are cosmic imposters, formed through entirely different processes than their neighbors? Or does dark matter weave itself into these structures in ways we haven't even begun to map? Every new observation deepens the mystery, proving once again that these ancient star swarms are far stranger than we ever imagined. If globular clusters were already cosmic oddities, their darkest secret might just be lurking in their cores, black holes of a size we never expected to find. For years, scientists assumed these dense star cities only hosted small stellar mass black holes, the remnants of collapsed stars. But then came Omega Centauri, a colossal globular cluster with a gravitational surprise at its heart. Hidden within its swirling mass of stars lies something far more monstrous, an intermediate mass black hole, a cosmic middleweight that defies easy explanation. These mysterious objects bridge the gap between the small black holes formed from dying stars and the supermassive beasts anchoring galaxies. What makes them so puzzling is their sheer rarity and the violent way they shape their surroundings. In Omega Centauri, astronomers noticed something uncanny: stars near the core whipping around at breakneck speeds, their orbits twisting as if tugged by an invisible heavyweight. The math didn't lie. Something with the mass of tens of thousands of suns had to be pulling them, something far denser than any star. The leading theory suggests these intermediate black holes might form through a brutal game of cosmic cannibalism. In the crowded core of a globular cluster, black holes could sink toward the center over time, merging together in a chain reaction of violent collisions. Imagine two black holes spiraling closer, locked in a gravitational dance until they finally crash, releasing ripples in spacetime and birthing a larger monster. Repeat that process over billions of years, and you might end up with a black hole massive enough to warp the entire cluster's structure. But the real shock comes when we see how these black holes reshape their neighborhoods. Stars straying too close get shredded, stretched, and torn apart in events called tidal disruption flares, lighting up the cluster with bursts of X-rays. Others get flung outward like cosmic slingshots, ejected from the cluster entirely at speeds that defy logic. And then there are the survivor stars locked in unstable orbits, their paths chaotic and unpredictable, as if the black hole is playing a game of gravitational billiards with them. Even stranger, not every globular cluster seems to host one of these rogue black holes. Some appear eerily quiet, their cores strangely placid, while others, like Omega Centauri, betray the presence of something monstrous. This inconsistency has astronomers scratching their heads. Are these black holes a natural byproduct of a cluster's violent history, or did some clusters form under special, extreme conditions that allowed these anomalies to exist? Every new observation peels back another layer, revealing just how little we truly understand about these ancient stellar metropolises. Globular clusters were once thought to be the ultimate single-generation retirement homes for stars, ancient populations born from the same primordial gas cloud, all sharing nearly identical chemical fingerprints. But when astronomers trained their spectrographs on these stellar cities, they found something that shattered that simple story. Stars with bizarrely high amounts of heavy elements like iron, barium, and even gold. These unusual chemical abundances shouldn't exist in such old systems, yet there they were, glittering contradictions hidden in plain sight. Take the cluster M22, where certain stars contain staggering amounts of elements typically forged in supernova or neutron star collisions. The puzzle: these chaotic, high-energy events should have been rare in the early universe when globular clusters formed. So how did these metals end up woven into the fabric of stars that, by all rights, should have been born pure? The answer might lie in a cosmic recycling program older than our solar system. Here's where things get wild. Some clusters appear to have hosted not one but multiple waves of star formation, a celestial generational divide. The first generation of stars, born from pristine hydrogen and helium, lived fast, died young, and exploded in supernova that polluted the cluster's remaining gas with heavy elements. Then, millions of years later, new stars condensed from this enriched material, carrying those exotic signatures in their atmospheres like cosmic birthmarks. That's why we see stars side by side in these clusters with wildly different compositions, some nearly metal-free, others glittering with the spoils of their predecessors' violent deaths. But the real head-scratcher comes from clusters like NGC 6535, where certain stars show elements like europium and platinum in ratios that defy known astrophysical processes. These anomalies suggest something even stranger: that globular clusters might have siphoned material from outside their boundaries, perhaps stripping gas from dwarf galaxies they encountered or capturing wandering clouds of metal-rich debris. It's as if these clusters didn't just evolve in isolation, they were cosmic scavengers hoarding heavy elements from whatever crossed their path. The implications are profound. If globular clusters can harbor multiple generations of stars, it means they weren't just frozen relics of the early universe, they were dynamic, evolving ecosystems. Some might have even hosted brief eras of frenzied star birth, with later generations forming under conditions far different from their ancestors. This challenges the very definition of what a globular cluster is, blurring the line between them and younger, more chemically complex structures like dwarf galaxies. And let's not forget the rogue stars, those with such extreme chemical signatures that they seem to have formed in environments unlike anything we've seen elsewhere. One theory suggests they might be the remnants of disrupted star systems, their peculiar compositions forged in the hearts of long-dead stars that met violent ends. Others propose they're evidence of exotic nuclear processes we haven't yet discovered, hidden deep within these ancient stellar metropolises. What's clear is this: the chemistry of globular clusters is anything but simple. These star cities are cosmic alchemists' labs, where generations of stars have cooked up elements in ways we're only beginning to decode. Every unusual spectral line, every unexpected metal-rich star is a clue, a whisper from the early universe about how matter transforms under the most extreme conditions imaginable. And with each new discovery, we're forced to rewrite the story of how these enigmatic clusters came to be. Astronomers studying globular clusters noticed something bizarre. Where were all the red giants? These swollen, aging stars should have been everywhere in these ancient stellar cities, burning brightly as they reached the final stages of their lives. Yet in clusters like Messier 10 and NGC 6397, researchers kept coming up short, far fewer red giants than their models predicted, as if entire generations of stars had vanished without explanation. This cosmic disappearing act forced scientists to reconsider what we thought we knew about how stars evolve in these densely packed environments. The mystery deepens when we examine the numbers. In a typical globular cluster, roughly 20% of stars should be red giants based on their age. But in some, like NGC 6808, that number plunges below 10%. So where did the missing stars go? One startling possibility is that these clusters aren't just aging gracefully, they might be actively dismantling themselves from within. The extreme gravitational environment near a cluster's core could be flinging red giants outward at high speeds, ejecting them before they ever reach their full luminous potential. Imagine a stellar retirement home where the elderly keep getting mysteriously shoved out the back door. But gravity isn't the only suspect. Another theory suggests these missing giants might be victims of cosmic vampirism. In the crowded interiors of globular clusters, stars often orbit in tight binary pairs. A red giant's outer layers, puffed up and loosely bound, could be siphoned away by a voracious companion star, stripping it down to its core before it ever shines as brightly as predicted. The result, a prematurely exposed stellar ember like a helium white dwarf, masquerading as a younger, smaller star. Perhaps the strangest clue comes from chemical anomalies in the remaining red giants. Some show unexpected dips in elements like carbon and oxygen, telltale signs of deep mixing processes that shouldn't occur under standard stellar models. It's as if the extreme density of these clusters triggers chaotic interior reactions, causing stars to burn their fuel in unconventional ways. This could explain why some red giants never grow as large or luminous as expected. They're essentially self-destructing from the inside out. The implications ripple far beyond globular clusters. If stars in these environments age differently than those in isolation, it forces us to rewrite entire chapters of stellar astrophysics. What other evolutionary shortcuts or dead ends might exist in the universe's most crowded neighborhoods? And if red giants can vanish without a trace, what else might we be missing in our cosmic census? Each absent giant is a silent witness to processes we're only beginning to comprehend, processes that might rewrite how we understand the life and death of stars everywhere. Among the countless stars packed into globular clusters, some don't stay put. They rocket outward at speeds so extreme they can escape the cluster entirely, streaking across the galaxy like cosmic outcasts. These runaway stars defy expectations, moving faster than anything gravity alone should allow, their trajectories telling tales of violent encounters and explosive origins. Take the case of a star dubbed J0927 in the cluster Messier 4. This white dwarf blazes through space at nearly 1,200,000 miles per hour, fast enough to cross the distance from Earth to the Moon in under 12 minutes. What could possibly launch a star with that much force? The leading suspect, a supernova kick. When a massive star explodes, the asymmetrical collapse of its core can act like a cosmic slingshot, hurling any surviving companion star outward at unimaginable speeds. Imagine being tethered to a bomb. When it detonates, the shockwave alone would fling you into oblivion. That's essentially what happens to these stellar survivors. But supernovae aren't the only culprits. In the crowded core of a globular cluster, stars often engage in gravitational pinball. When two binary star systems pass too close, their intricate dance can fling one star outward while the others spiral inward. The math behind these interactions is staggering. A single chaotic encounter can accelerate a star to over 100,000 miles per hour in seconds. Some runaways even show evidence of being part of a triple system before their explosive breakup, their chemistry revealing traces of companions they left behind in the chaos. The real surprise came when astronomers realized these escapees aren't just random casualties. They follow distinct patterns. Fast-moving stars tend to cluster along specific trajectories, like cosmic breadcrumbs pointing back to their birthplace. This allowed researchers to trace one group of runaways in the Omega Centauri cluster all the way back to a single, catastrophic event roughly 2 million years ago, likely a supernova or black hole interaction that sent shockwaves through the system. Even more bizarre, some runaway stars aren't solitary. Entire binary pairs have been found racing through space together, still gravitationally bound despite their shared traumatic ejection. What makes these stellar fugitives so valuable is what they carry with them: clues about the extreme environments they fled. Runaways from globular clusters often have unusual chemical compositions, their atmospheres bearing the marks of close encounters with neutron stars or black holes. Others show strange isotopic ratios, hinting at nucleosynthesis processes that only occur in the hearts of densely packed stellar systems. By studying these cosmic castaways, we're essentially collecting forensic evidence from a crime scene, one where the weapons were gravitational tides and thermonuclear explosions. The implications stretch far beyond globular clusters. If runaway stars can be launched with such force, they might be responsible for seeding heavy elements across the galaxy, effectively acting as interstellar couriers for materials forged in extreme environments. Some researchers speculate that a fraction of the high-velocity stars zooming through our galactic neighborhood might actually be ancient refugees from globular clusters, their origins obscured by millions of years of solitary travel. But the mystery doesn't end there. Recent observations have uncovered runaway stars moving so fast they shouldn't exist. Hypervelocity stars with speeds exceeding 1.5 million miles per hour, far beyond what traditional ejection mechanisms can explain. One theory suggests these extreme cases might involve interactions with intermediate mass black holes, their immense gravitational leverage capable of launching stars like cosmic cannonballs. Another proposes they're the survivors of rare triple-system breakups, where the complex interplay of gravity acts like a multi-stage rocket booster. Every runaway star tells a story of survival, a snapshot of the chaotic forces shaping these ancient stellar cities. As we track their paths through the galaxy, we're not just mapping trajectories, we're reconstructing histories of violence, betrayal, and escape on a scale that dwarfs any earthly saga. And with each new discovery, we're reminded that in the universe's oldest neighborhoods, tranquility is an illusion beneath the glittering surface. These clusters are battlegrounds where stars fight for freedom. Globular clusters were supposed to be textbook examples of stellar evolution, places where stars follow predictable paths from birth to death. But then astronomers noticed something peculiar. Certain clusters contained an overabundance of stars lingering in what's called the horizontal branch phase, burning helium in their cores far longer than standard models predicted. These extended horizontal branch stars became cosmic outliers, their prolonged glow defying expectations and forcing scientists to rewrite the rules of stellar aging. Take the cluster NGC 6760, where nearly 40% of stars were found stalled in this transitional phase, a percentage so high it sent researchers scrambling for explanations. Normally, stars spend only a brief period on the horizontal branch before evolving into red giants or cooling into white dwarfs. But in these clusters, something was pressing pause on stellar evolution itself. The leading suspect: rotation. Stars in globular clusters spin faster than their galactic counterparts, their rapid rotation altering internal pressure and slowing the rate at which they burn through helium. Imagine a spinning top that refuses to topple. These stars maintain their balance far longer than anticipated, their cores churning in ways we're only beginning to understand. Yet rotation alone doesn't solve the puzzle. Chemical composition plays a starring role too. Stars in these clusters often show unusual levels of elements like nitrogen and sodium, traces of deep mixing that reshuffle nuclear fuel and extend their horizontal branch lifetimes. It's as if these stars developed a form of cosmic CPR, recycling their own material to stay active longer. Some even exhibit bizarre splits in their horizontal branches, distinct subgroups burning at different temperatures, like parallel tracks of stellar evolution playing out simultaneously within the same cluster. The most tantalizing clue comes from clusters with extreme stellar densities. In these crowded environments, close encounters between stars may trigger tidal forces that alter their internal structure, effectively stirring their cores and delaying their inevitable transition off the horizontal branch. Picture a pot of water boiling, give it a vigorous stir, and the heat distributes differently. Stars subjected to gravitational jostling might experience similar disruptions, their nuclear furnaces burning unevenly as a result. What's truly mind-bending is how these anomalies challenge the very definition of stellar age. Two stars born at the same time with identical masses can end up on wildly different evolutionary paths simply because one resides in a globular cluster and the other drifts alone through the galaxy. It's a reminder that context matters. The environment of a star can rewrite its destiny as surely as its initial mass. And if we've misjudged how stars behave in these dense clusters, how many other cosmic assumptions might need revisiting? The extended horizontal branch phenomenon isn't just a curiosity, it's a window into the complex interplay of physics, chemistry, and motion that governs stellar life cycles. Each prolonged glow from these rebel stars carries coded information about the turbulent histories of their parent clusters, hinting at past collisions, mergers, or waves of star formation we've yet to uncover. As astronomers decode these signals, they're piecing together a new narrative, one where stars don't just passively age, but actively negotiate their fates with the universe around them. Globular clusters don't just host single stars, they're cosmic stages for intricate stellar dances, where pairs of stars orbit each other so closely they can swap material like celestial thieves in the night. The sheer number of binary systems in these dense star cities is staggering, up to 50% more than in our galactic neighborhood, and their gravitational waltzes lead to some of the most bizarre phenomena in the universe. Take the case of a binary system in the cluster Terzan 5, where a pulsar, a rapidly spinning neutron star, is locked in orbit with a companion so close that it's steadily siphoning material away. This stolen gas doesn't just disappear, it accumulates on the pulsar's surface until the pressure triggers thermonuclear explosions, lighting up the cluster with X-ray flares visible across interstellar distances. It's a cosmic seesaw of destruction and rebirth, where one star's loss becomes another's violent gain. But the real shock comes from blue straggler factories, binary systems that serve as stellar rejuvenation clinics. When two stars orbit tightly enough, the larger one can expand and spill its outer layers onto the smaller companion, essentially transferring its youthful energy. The recipient star absorbs this material, growing hotter and bluer while its donor shrinks into a faint, exhausted core. This process can create stars that look billions of years younger than their surroundings, like cosmic imposters hiding in plain sight. Even wilder are the cataclysmic variables, binary pairs where a white dwarf star strips gas from its partner so aggressively that the stolen material forms a searing disk around it. Every few decades, this disk becomes unstable and detonates in a runaway thermonuclear reaction, temporarily outshining the entire cluster. These eruptions scatter heavy elements like iron and nickel into space, leaving behind chemical fingerprints that astronomers can trace millions of years later. The gravitational dynamics of these systems are mind-bending. Some binaries orbit so fast they complete a full revolution in less than an hour, stars whipping around each other at speeds approaching 1% of light speed. Others exhibit bizarre heartbeat light curves where their mutual gravity distorts their shapes with each pass, causing rhythmic pulses in brightness detectable across the galaxy. What makes globular clusters special is how frequently these extreme binaries form. In the crowded core, stars are constantly nudged closer together by gravitational interactions, creating pairings that would be vanishingly rare elsewhere. These forced marriages lead to stellar relationships that push the limits of physics systems where stars exchange mass like trading cards, where orbits decay into violent mergers, and where the line between two stars and one becomes blurred beyond recognition. Yet the biggest mystery isn't how these binaries behave. It's why some clusters are absolutely teeming with them while others have surprisingly few. This variation hints that these ancient star cities might have formed under radically different conditions, with some emerging from gas clouds already rich in paired stars while others forged their binaries through later gravitational encounters. Each cluster tells its own story through these celestial couple stories of theft, survival, and transformation written in the language of orbiting light. Deep in the hearts of globular clusters, there's a cosmic detective story unfolding, one involving an element that's mysteriously vanishing before our eyes. Lithium, the third lightest element in the universe, should be abundant in these ancient stars. Yet when astronomers peered into their atmospheres, they found something startling. Up to 90% of the expected lithium was missing, as if some unseen force had erased it from existence. This isn't just a minor discrepancy, it's a gaping hole in our understanding of stellar chemistry, one that hints at processes we've never witnessed. Take the star known as Messier 42148, for example. Born nearly 13 billion years ago, it should be a pristine relic of the early universe, its lithium content frozen in time like a cosmic time capsule. Instead, it shows lithium levels 50 times lower than predicted, as if something had systematically scrubbed the element from its outer layers. The puzzle deepens when we compare clusters. Some, like NGC 6397, have stars with almost no lithium at all, while others, like Messier 4, retain just a fraction of what models suggest. This inconsistency rules out simple explanations, pointing instead to a complex interplay of physics unique to these dense stellar environments. So where does the lithium go? One theory involves stellar interiors behaving like cosmic shredders. In normal stars, lithium sits safely in the cooler outer layers, protected from the furnace below. But globular cluster stars might experience extreme mixing, their inner turbulence dredging up material from deep within, where temperatures soar high enough to destroy lithium nuclei on contact. Imagine a blender churning through the star's layers, bringing lithium down into regions so hot that protons tear the fragile atoms apart. This process, known as thermohaline mixing, could explain the depletion if it happens more violently in clusters than elsewhere. Yet there's a twist. Some stars show lithium depletion only in certain phases of their lives. Red giants, for instance, often exhibit sudden lithium drops as they expand, suggesting their swelling outer layers become more efficient at destroying the element. But in clusters, even main sequence stars, those still burning hydrogen steadily, show these anomalies, meaning the mechanism can't just be tied to late-stage stellar evolution. This forces astronomers to consider even stranger possibilities, like magnetic fields playing an unexpected role. Strong stellar magnetism might create dead zones where lithium gets trapped and destroyed, or it could accelerate mixing processes beyond what we see in isolated stars. The most tantalizing clue comes from stars that briefly regain lithium before losing it again, like cosmic magicians pulling elements from a hat only to make them vanish once more. These rare cases suggest lithium might sometimes be synthesized in stellar atmospheres through poorly understood nuclear reactions, only to later fall victim to destruction mechanisms. It's as if these stars are locked in a cyclical battle between creation and annihilation, one where destruction usually wins. What makes this mystery so critical is what it reveals about the early universe. Lithium was forged in the Big Bang alongside hydrogen and helium, making its absence a direct challenge to our models of cosmic chemical evolution. If globular clusters, some of the oldest structures we can study, are systematically destroying lithium, it could mean we've overestimated how much of the element existed in the primordial universe. That has staggering implications, potentially forcing us to revise our understanding of nucleosynthesis itself. But perhaps the strangest realization is this: the missing lithium might be teaching us less about stars and more about the invisible forces shaping them. The variations between clusters suggest that environmental factors, things like stellar density, magnetic field strength, or even the presence of binary companions, might control lithium's fate in ways we're only beginning to map. Each lithium-poor star is therefore a messenger, carrying encrypted information about the hidden physics governing these ancient stellar metropolises. And until we crack its code, a fundamental piece of cosmic history remains just out of reach. Among the invisible light shows playing out in globular clusters, few are as puzzling as the gamma-ray excess emanating from places like 47 Tucanae, a celestial beacon of high-energy radiation that shouldn't exist at such intensity. These gamma-rays, detected by space telescopes like Fermi, arrive with energies that defy straightforward explanation, sparking a debate that pits exotic dark matter against the more mundane but no less fascinating physics of spinning stellar corpses. At first glance, the culprit seems obvious: pulsars, these ultra-dense neutron stars left behind after supernova explosions, spin at dizzying speeds, sweeping beams of radiation across space like cosmic lighthouses. In a crowded environment like 47 Tucanae, home to potentially thousands of these objects, their combined emissions could theoretically produce the observed gamma-ray glow. But there's a hitch. When astronomers tallied up the known pulsars in the cluster, their total output fell far short of the detected signal. Either we're missing a hidden population of these stellar zombies, or something else is at work. Enter dark matter. One provocative theory suggests that these gamma rays could be the death throes of weakly interacting massive particles, WIMP, the hypothetical building blocks of dark matter. According to this idea, when two WIMP collide in the dense core of a globular cluster, they might annihilate each other in a burst of energy, with gamma rays as the telltale byproduct. 47 Tucanae, with its immense gravitational pull, would act like a dark matter trap, concentrating these particles enough to make such collisions frequent. It's a tantalizing possibility, offering a rare window into the invisible 85% of matter in the universe. Yet the plot thickens when we examine the gamma-ray distribution. Unlike the smooth signal expected from dark matter annihilation, the emissions from 47 Tucanae appear patchy, concentrated in specific areas rather than spread evenly throughout the cluster. This irregularity points back to astrophysical sources like pulsars, whose emissions would naturally clump where these objects are most densely packed. Some researchers argue we're seeing a mix of both phenomena, a baseline of pulsar activity peppered with occasional dark matter fingerprints, creating a composite signal that's devilishly hard to untangle. The stakes couldn't be higher. If this gamma-ray excess truly stems from dark matter, it would be the first direct evidence of its particle nature, revolutionizing our understanding of the cosmos. But even if pulsars are solely responsible, the implications are profound. It would mean globular clusters harbor far more of these extreme objects than we've accounted for, likely hidden in binary systems or obscured by debris. Each unanswered question drives astronomers to develop more sensitive detectors and refined models, peeling back layers of this high-energy mystery one observation at a time. What makes this enigma so compelling is how it embodies the dual nature of globular clusters, simultaneously laboratories for known physics and playgrounds for the unknown. Whether the answer lies in the mundane or the exotic, these ancient star cities continue to challenge our assumptions, proving once again that the universe keeps its most fascinating secrets hidden in plain sight. Peering into the hearts of globular clusters reveals a cosmic sorting mechanism at work. Some boast cores so densely packed they resemble stellar traffic jams, while others appear oddly hollowed out at their centers. This striking variation stems from a process called dynamical friction, an invisible cosmic sculptor reshaping these star cities over billions of years. Picture two stars passing in the crowded core. The more massive one tugs harder on its surroundings, losing momentum as it plows through a sea of lighter neighbors like a bowling ball rolling through sand. Over time, this drag steers heavyweight stars inward while flinging lighter ones outward, a gravitational sorting algorithm that concentrates mass at the cluster's heart. The speed of this transformation depends on the cluster's initial conditions. Take Omega Centauri, whose core brims with stars crammed 1,000 times tighter than in our solar neighborhood. Here, dynamical friction worked relentlessly, pulling so many massive stars inward that they nearly collapsed into a single chaotic knot. Contrast that with Palomar 5, a ghostly cluster with a diffuse core where stars wander loosely. Its sparse population meant friction operated too slowly to concentrate mass before outside forces began tearing it apart. The difference between these extremes comes down to a simple but powerful equation. The more stars per cubic light year, the faster dynamical friction reshapes the core. But there's a twist: this process doesn't continue indefinitely. At peak density, something extraordinary happens. Binary stars become the cluster's gravitational shock absorbers. When two stars lock in close orbit, their combined gravity can slingshot passing singles outward in elastic collisions, pumping energy back into the core and halting its collapse. This stellar feedback loop creates equilibrium in clusters like Messier 15, where the core reaches incredible density but refuses to collapse further, as if an invisible force field surrounds its heart. The real wild card comes from black holes. Simulations show that if enough stellar mass black holes sink to the center products of dead massive stars, their extreme gravity can dominate the core's evolution. Some clusters may eject these dark remnants through gravitational encounters, leaving behind a puffed-up core, while others retain them as anchors that accelerate core collapse. The presence or absence of just a few dozen black holes could determine whether a cluster develops an ultra-dense nucleus or remains loosely structured. This cosmic balancing act leaves behind forensic evidence. Core-collapsed clusters often show skewed stellar populations, their centers depleted of lightweight stars that got ejected during the sorting process. Others exhibit bizarre velocity patterns, with stars near the core whipping around faster than expected, their motions betraying the gravitational scars of past dynamical upheavals. These clues let astronomers reconstruct each cluster's unique history, revealing whether it underwent rapid collapse, achieved equilibrium, or got disrupted by galactic tides before the process could complete. What makes this conundrum so fascinating is how it connects to the cluster's lifespan. Ultra-dense cores act like gravitational batteries, storing energy that can power a cluster's survival for eons. Yet they also become stellar pressure cookers, regions where close encounters fling stars outward like cosmic popcorn, gradually evaporating the cluster into the galaxy. The same force that gives these ancient structures their dazzling centers may ultimately spell their demise. Globular clusters harbor some of the strangest real estate in the cosmos: planets that orbit the dead, spinning remnants of exploded stars. These pulsar planets shouldn't exist. When a massive star goes supernova, the blast should vaporize any nearby worlds, yet against all odds, astronomers have detected them. Alien environments bathed in relentless particle beams and gravitational chaos. Take PSRB 1620-26, a pulsar in the cluster Messier 4 with at least one planet clinging to it. This world survived the violent death of its parent star, enduring a supernova so powerful it should have ripped any orbiting bodies to shreds. Instead, the planet persisted, either by being flung into a distant orbit during the explosion or forming afterward from the debris. Now it orbits a stellar corpse that spins 600 times per second, bombarding it with enough high-energy radiation to strip atmospheres and fry surfaces in seconds. The fact that any planetary material could endure these conditions rewrites our understanding of cosmic resilience. Even more baffling is how these planets might form. One theory suggests they're the salvaged cores of gas giants, their outer layers blasted away, leaving behind dense rocky remnants. Another proposes they coalesced from the supernova's fallout, a disk of heavy elements like iron and gold forged in the star's final moments. In the cluster NGC 6752, a pulsar designated PSRJ 1023 plus 0038 even hints at multiple worlds, their gravitational tugs subtly altering the pulsar's precise spin. The most famous pulsar planet, discovered orbiting PSRB 1257 plus 12 in the Virgo cluster, showcases just how exotic these worlds can be. Calculations suggest it might be mostly composed of crystalline carbon, a diamond the size of a planet, forged under extreme pressures as its parent star collapsed. But the real surprise came when researchers detected possible traces of a second, smaller companion locked in a bizarre dance. Its orbit so elliptical that it swings between scorching proximity and icy distance over time. These systems challenge everything we know about planetary habitability. While no life could survive the particle storms and intense magnetic fields engulfing pulsar planets, their mere existence proves that planets can form in environments we once considered utterly hostile. Some might even be refugees' worlds originally belonging to other stars in the cluster, captured by pulsars during close gravitational encounters. Others could be the shattered remains of binary companions, their material reorganized into new configurations after catastrophic disruptions. What's clear is this: pulsar planets represent the ultimate survivors, enduring conditions that obliterate most matter. Their discovery forces us to expand our definition of what a planet can be and where we might find them. As we uncover more of these cosmic oddities, we're not just cataloging strange worlds. We're piecing together the aftermath of stellar apocalypses, one irradiated orbit at a time. Globular clusters don't always stay loyal to their home galaxies. Sometimes they're stolen in the ultimate cosmic heist. Across billions of years, galaxies like the Milky Way engage in gravitational tug-of-wars, ripping entire clusters away from their neighbors and claiming them as their own. This celestial theft isn't just about bragging rights. It reshapes the very fabric of both the thief and the victim, leaving behind clues in the cluster's chemistry and orbits. Take the case of Omega Centauri, the largest globular cluster orbiting our galaxy. For decades, astronomers puzzled over its bizarre traits, its sheer size, its multiple generations of stars, and its unusual motion. Then came the revelation: this isn't just a cluster. It's likely the surviving core of a dwarf galaxy the Milky Way devoured long ago, stripped of its outer stars until only its glittering heart remained. The evidence is written in the stars themselves, some with chemical signatures matching no other Milky Way cluster, hinting at an origin in a completely different cosmic environment. But Omega Centauri isn't alone. The galaxy's outer halo is littered with clusters on wild, looping orbits, stellar refugees from past collisions. One group, the Gaia Sausages, traces back to a dramatic merger 8 to 10 billion years ago when a smaller galaxy smashed into the Milky Way, its clusters scattered like cosmic shrapnel. These stolen clusters don't blend in. Their metallicities and ages often stand out starkly against the Milky Way's native population, like guests who arrived late to the party wearing entirely different attire. The mechanics of these thefts are surprisingly violent. When galaxies pass too close, their gravitational interplay creates tidal streams, rivers of stars and clusters stretched out by competing pulls. The weaker galaxy gets shredded, its clusters either flung into intergalactic space or captured by the victor. Some clusters, like those in the Sagittarius dwarf galaxy, are currently being torn away in slow motion, their stars leaving glowing trails across the sky as the Milky Way consumes them bite by bite. What's truly mind-bending is how these stolen clusters betray their pasts. Those swiped from gas-rich galaxies often host more heavy elements, forged in their original home's prolific star-forming regions. Others, like the metal-poor clusters in the Milky Way's outer halo, might be relics of the universe's first galaxies, pristine time capsules hijacked during the cosmos' most chaotic era. Even their orbits tell stories. Tight, circular paths suggest peaceful assimilation, while wild, elongated trajectories scream of violent encounters. The implications ripple far beyond our galaxy. In the distant Virgo cluster, astronomers have spotted entire clouds of globular clusters unmoored from any galaxy, floating like cosmic nomads after being ripped away in ancient collisions. Some might eventually find new homes, others will drift forever in the darkness, their origins fading into obscurity. This great cluster heist isn't just history, it's still happening. The Milky Way is on course to collide with Andromeda in 4 billion years, and when it does, their clusters will be tossed like dice in a gravitational craps game. Some may escape entirely, launched into the void by the chaos. Others will switch allegiances, their stellar populations mixing beyond recognition. It's a reminder that in the universe, nothing is truly permanent, not even the bonds between galaxies and their oldest stellar companions. What if some globular clusters aren't made of stars at all? The idea sounds like science fiction, but recent discoveries hint at something eerie, shadowy structures hiding in plain sight, their gravitational pull betraying their presence while their light remains stubbornly absent. These invisible clusters could be cosmic ghosts, their stars long since vanished, leaving behind only dark matter or a dense swarm of black holes to mark where they once shone. Take the case of a peculiar gravitational anomaly near the Andromeda galaxy. Astronomers tracking star movements noticed a region where celestial objects curved their paths as if tugged by an unseen mass, yet no visible cluster matched the signal. The most plausible explanation, a dark globular cluster, its stars either evaporated over billions of years or never formed to begin with. Simulations suggest such structures could exist if dark matter clumped densely enough in the early universe, creating gravitational wells too shallow to ignite starbirth but deep enough to persist as invisible halos. Then there's NGC 6139, a cluster that appears strangely underweight for its size. Its stars move as if bound by far more mass than telescopes can account for, leading some researchers to propose that nearly half its bulk might come from an unseen population of stellar mass black holes. If true, it raises a tantalizing question. Could some clusters evolve to become black hole dominions, their stars gradually ejected or consumed until only dark remnants remain? The mechanics behind this transformation are as brutal as they are fascinating. In a typical globular cluster, black holes, born from massive star collapses, sink toward the core over time, their gravity slingshotting lighter stars outward. Eventually, the cluster's center could become so packed with black holes that they begin merging or ejecting each other through gravitational kicks, leaving behind a diffuse, starless husk. Some models even predict clusters where thousands of black holes orbit in a nightmarish gravitational dance, their combined mass warping spacetime but emitting no light to betray their presence. But the real twist comes from dark matter's potential role. While most globular clusters seem to lack significant dark matter halos, a handful of outliers like NGC 2410 show gravitational anomalies that resist explanation by visible mass alone. Could these be the last survivors of a forgotten population of dark matter-dominated clusters, formed in the early universe under conditions we've yet to replicate in simulations? Or are we seeing the aftermath of collisions between clusters and dark matter subhalos, events that left behind ghostly imprints in the stellar motions? The hunt for these phantom clusters is pushing astronomy to its limits. New techniques like gravitational microlensing, where invisible objects betray themselves by bending light from background stars, have turned up mysterious compact masses in galactic halos, some with densities matching theoretical dark globulars. Others search for telltale gamma-ray flashes from hypothetical dark matter particle annihilations in these regions, hoping to catch a glimpse of physics beyond the standard model. What's at stake isn't just a cosmic curiosity. If starless clusters exist, they could solve lingering mysteries about galaxy formation, dark matter distribution, and even the fate of the universe's first stellar structures. They might serve as dark matter laboratories, their isolated environments offering pristine conditions to study its properties. Or they could rewrite the story of how globular clusters evolve, proving that even the universe's most glittering cities can fade into darkness. Until we find definitive proof, these invisible giants remain one of astronomy's most tantalizing what-ifs, a reminder that the cosmos still keeps its darkest secrets well hidden. Globular clusters are supposed to be the senior citizens of the cosmos, relics from the universe's wild teenage years over 10 billion years ago. But then there's the baffling case of NGC 2173, a cluster that looks like it crashed the retirement party. While most of its peers show their age with ancient metal-poor stars, this one gleams with the vigor of a system barely 2 billion years old, making it a cosmic toddler by comparison. Its existence throws a wrench into our understanding of how and when these stellar cities form, forcing astronomers to ask, did this cluster cheat time, or are we missing a whole chapter in their origin story? The mystery deepens when you examine its stellar population. Unlike typical globulars, where stars share nearly identical ages and compositions, NGC 2173 hosts multiple generations, some stars still burning bright with youthful energy while others show subtle signs of aging. This isn't just unusual, it's practically unheard of in classical globular clusters. The leading theory, this outlier might not have formed in the early universe at all, but instead was born during a later, isolated burst of star formation, perhaps triggered by a galactic collision or a rogue gas cloud's collapse. Imagine a medieval village suddenly sprouting skyscrapers. NGC 2173 defies the expected architectural rules of its kind. Even stranger is its location. Most ancient globular clusters orbit in the halos of galaxies, but this youthful rebel sits much closer to the turbulent disk of the Large Magellanic Cloud, a satellite galaxy of the Milky Way. Here, it's bathed in the kind of gas and dust that normally fuels new star birth conditions that vanished from the universe's quieter suburbs billions of years ago. Some researchers argue it's not a true globular at all, but a massive open cluster that got lucky, ballooning to globular-like size through a perfect storm of dense star formation. Others propose it's evidence of a forgotten formation pathway, where clusters can sometimes bootstrap themselves into existence long after the cosmic dawn. The real bombshell came when astronomers compared it to other oddballs like NGC 185 in Andromeda and Lindsay 1 in the small Magellanic Cloud clusters that also laugh in the face of traditional age estimates. Together, they form a rogues gallery of youthful imposters, each challenging the idea that all globulars are fossils from a single era. Their chemistry adds another layer of intrigue. While ancient clusters are notoriously metal-poor, these young rebels show traces of heavier elements, suggesting they formed from gas already enriched by earlier generations of stars. It's like finding a modern smartphone buried in a pharaoh's tomb. The timeline just doesn't add up. Could these outliers be the key to a deeper truth? Some scientists now speculate that globular clusters aren't a monolith but a spectrum, with multiple formation mechanisms that span cosmic history. Perhaps the classic ancients were indeed born in the universe's first chaotic billion years, while younger clusters like NGC 2173 represent a second wave, forged during rare late-stage conditions that mimic the early universe's frenzy. Others wonder if we're seeing the handiwork of galactic mergers, clusters formed in dwarf galaxies that were later absorbed, preserving their younger ages like insects trapped in amber. The implications ripple far beyond stellar demographics. If globular clusters can form across such vast stretches of time, it reshapes how we interpret their role in galactic evolution. Young clusters might be actively shaping their environments today, their massive stars pumping radiation and metals into surrounding gas, while ancient ones serve as silent witnesses to bygone eras. This duality forces us to reconsider everything from dark matter distribution to the timeline of galaxy assembly, all because a few rebellious clusters refuse to act their age. As telescopes probe deeper into nearby galaxies, each new discovery blurs the line between globular and non-globular clusters further. NGC 2173 and its youthful kin aren't just outliers, they're cosmic provocateurs, daring us to rewrite the rulebook on how star clusters live, die, and occasionally defy time itself. Globular clusters have long been considered celestial monolith stellar siblings born from the same primordial gas cloud, sharing identical chemical signatures like cosmic twins. But when astronomers began analyzing these ancient star cities with modern spectrographs, they uncovered a truth that shattered this simple story. Many clusters host multiple distinct populations of stars, each with wildly different chemical fingerprints. It's as if someone took a meticulously organized family photo and spliced in strangers from another galaxy, creating a cosmic mosaic that defies explanation. Take the massive cluster Omega Centauri, where stars coexist with iron abundances varying by a factor of 10, some nearly pristine, others enriched with heavy elements like they'd been bathing in supernova debris. This isn't just a minor discrepancy, it's evidence of a turbulent birth environment where star formation happened in waves, each new generation inheriting the chemical pollution of its predecessors. The most striking examples are the sodium-rich stars found in clusters like NGC 6760, where certain stars contain 20 times more sodium than their neighbors, their atmospheres betraying exposure to extreme nuclear processing that shouldn't occur in such ancient systems. So how did these multiple populations arise? The leading theory paints a chaotic picture. Clusters might have formed in 2 or more bursts, with later generations condensing from gas contaminated by the violent deaths of the first stars. Imagine a stellar nursery where massive stars live fast, explode young, and spew elements like oxygen, magnesium, and aluminum into the remaining gas. When new stars form from this enriched material, they carry these chemical imprints like cosmic birth certificates. But the mystery deepens when we find stars with opposing traits, some rich in helium but poor in carbon, others packed with nitrogen but devoid of oxygen. These aren't just random variations, they're chemical dichotomies pointing to separate formation events under wildly different conditions. The real curveball comes from clusters like Messier 15, where certain stars show anti-correlated element patterns. When one element spikes, another plummets, as if some invisible process selectively filtered atoms during their formation. One explanation involves polluter stars, massive, short-lived progenitors whose winds or explosions injected specific elements into the cluster's gas before the next generation formed. But even this doesn't account for the sheer diversity seen in some clusters, where stars split into 3, 4, or even 5 distinct chemical groups. Perhaps the most fascinating clue lies in the spatial distribution of these populations. In many clusters, the chemically enriched stars crowd the core, while the pristine ones dominate the outskirts, a clear sign that dynamics played a role in segregating them over billions of years. This suggests that what we're seeing isn't just a record of star formation, but a gravitational sorting algorithm at work, with heavier, metal-rich stars sinking toward the center while lighter ones migrate outward. The implications ripple far beyond globular clusters. If these ancient structures can harbor such chemically diverse stars, it challenges our understanding of how star-forming environments operate in the early universe. Were these clusters once embedded in larger gas clouds that fueled multiple epochs of star birth? Did they cannibalize smaller stellar systems, absorbing their distinct populations? Or does their complexity hint at entirely overlooked physics governing how stars condense from turbulent, polluted gas? With each new observation, these multiple populations grow more enigmatic. They're not just scientific curiosities, they're encrypted messages from the universe's formative years, waiting to reveal how the first stellar cities built themselves from chaos. And as we decode their chemical hieroglyphics, we're not just rewriting the history of globular clusters, we're glimpsing the untold stories of how complexity emerged in the infant cosmos. Globular clusters may appear as tight, symmetrical spheres, but look closer. Many are slowly unraveling, their stars being plucked away by invisible forces to form shimmering rivers of light across the cosmos. These tidal tails, stretching hundreds of thousands of light years in some cases, are the aftermath of a relentless gravitational tug-of-war between clusters and their host galaxies. Picture a cosmic spiderweb, its delicate strands tracing where stars once belonged, a ghostly reminder of the violence simmering beneath the universe's serene facade. The process begins with a cluster's orbit. As it swings close to a galaxy's dense core, the difference in gravitational pull, stronger on the near side, weaker on the far side, stretches the cluster like taffy. Over eons, stars caught in these tidal forces are peeled away, forming two distinct streams, one leading the cluster's path, the other trailing behind. In the case of Palomar 5, nearly half its original mass has been siphoned off into tails that now stretch across 20 degrees of sky, enough to link the Big Dipper's bowl to Polaris if visible to the naked eye. What makes these tidal tails so valuable is what they reveal. Like breadcrumbs, their starry trails map a cluster's orbital history, exposing past encounters with galactic arms, dark matter clumps, or even other clusters. The tails of NGC 5466, for instance, twist like corkscrews, betraying a chaotic journey through the Milky Way's turbulent halo. Others, like those emanating from the cluster M68, appear razor-straight, suggesting a quieter existence far from disruptive influences. But the real surprise lies in what these streams contain. Tidal tails aren't just random scatterings of stars, they're cosmic sorting machines. Lighter stars get ejected more easily, leaving behind a cluster increasingly dominated by heavyweights. Some tails even harbor rogue planets or orphaned binary systems flung out during the disruption, drifting in darkness far from their birthplace. The most astonishing examples challenge our understanding of cluster resilience. The Phoenix Stream, a ribbon of stars winding through the southern sky, shows no visible progenitor cluster at all, just the remnants of one completely dissolved by tidal forces. It's a celestial crime scene where the victim has vanished, leaving only stellar debris as evidence. Meanwhile, the GD1 stream in the Milky Way's halo gaps like a broken necklace, its stars mysteriously absent along a segment, possibly ripped away by a close encounter with a dark matter subhalo. These phenomena aren't just destructive, they're creative. Tidal tails may seed galaxies with free-range stars, contributing to their halo's diffuse glow. Some researchers speculate that certain oddball stars in our solar neighborhood, those with unusual velocities or compositions, might be refugees from clusters that unraveled billions of years ago. Others propose that the darkest tails, those stripped entirely of gas and dust, could be ideal hunting grounds for rogue black holes or dark matter clumps, their pristine environments making gravitational anomalies easier to spot. As telescopes like Rubin Observatory come online, their panoramic views will reveal thousands more tidal streams, each a frozen snapshot of gravitational physics in action. Far from being endpoints, these shimmering trails are just the beginning, a roadmap to understanding how galaxies and their clusters evolve together, bound by forces that both build and destroy across cosmic time. Globular clusters glow with more than just starlight, some pulse with intense X-rays, revealing violent encounters hidden within their ancient cores. While these star cities appear serene from afar, space telescopes like Chandra have uncovered bizarre X-ray sources flaring unpredictably, their origins tied to some of the most extreme physics in the universe. The leading suspects, neutron stars and white dwarfs caught in cosmic duels where gravity warps space and matter, get shredded at atomic scales. Consider the case of NGC 6397, where a single X-ray source outshines the combined light of every other object in the cluster. This isn't just a flickering ember, it's a neutron star guzzling gas stolen from a companion, heating the stolen material to millions of degrees until it screams in X-rays. But what makes these systems so startling is their scarcity. In a cluster packed with hundreds of thousands of stars, only a handful of these X-ray binaries exist, implying something rare and catastrophic must forge them. The process begins when two stars, often a neutron star and a bloated red giant, get locked in a tight gravitational embrace. As the giant swells, its outer layers spill toward the neutron star, forming a swirling disk of superheated plasma. But here's where things get chaotic. The neutron star's immense gravity doesn't just pull gently, it rips gas away in clumps, creating torrents of matter that slam into its surface at near light speed. Each impact triggers thermonuclear explosions detectable across interstellar space, flickering like a cosmic strobe light. White dwarfs add another layer of intrigue. In clusters like 47 Tucanae, astronomers have spotted pairs of these dense stellar corpses whirling around each other so closely that they're destined to collide. When they finally merge, the resulting explosion could rival a supernova, flooding the cluster with X-rays as heavy elements like gold and platinum forge in the blast. Some models even suggest these mergers might birth peculiar, hybrid stars objects with neutron star cores wrapped in white dwarf material, defying standard stellar classifications. Yet the real mystery lies in the outliers, X-ray sources that defy categorization. One object in Messier 22 emits X-rays at energies so high they imply a black hole might be involved, even though no stellar mass black hole has been confirmed in the cluster. Another, in Omega Centauri, flares erratically, as if an unseen object is periodically dumping matter onto a hidden companion. These anomalies hint at populations of dark, compact objects lurking in clusters, their presence betrayed only by occasional bursts of high-energy radiation. The implications stretch beyond mere curiosity. Each X-ray flash acts as a tracer for dynamic processes unseen in visible light, revealing how globular clusters redistribute energy and matter over eons. Some researchers speculate these systems could be factories for gravitational waves, their tight binaries destined to spiral together in collisions that ripple spacetime itself. Others suggest the X-ray emissions might influence entire clusters, heating ambient gas and altering the trajectories of nearby stars. What's clear is that these high-energy phenomena are more than cosmic fireworks. They're vital clues to understanding how matter behaves under conditions impossible to recreate on Earth. Every flickering X-ray source tells a story of survival, theft, and destruction, written in the language of atoms torn apart and reassembled in the universe's most extreme environments. And with each new detection, we're reminded that even the oldest structures in the cosmos still harbor secrets waiting to erupt in bursts of invisible light. Among the countless stars burning through their final stages in globular clusters, a bizarre subgroup defies every expectation. Stars that should be cooling into retirement suddenly reverse course, heating back up as if cosmic clocks were running backward. These blue hook stars, named for their abrupt leftward turn on color magnitude diagrams, represent one of stellar evolution's greatest puzzles. While normal stars follow predictable paths from hydrogen burning to red giant expansion, these rebels take a sharp detour, looping back toward hotter temperatures when they should be fading into obscurity. The phenomenon was first spotted in clusters like Omega Centauri and NGC 2801, where certain stars clustered in a region astronomers dubbed the extended horizontal branch, a zone where no stars should logically exist. Their spectra revealed surface temperatures soaring above 50,000 Kelvin, hotter than many newborn stars, yet their chemical fingerprints betrayed advanced ages. The leading explanation involves a stellar midlife crisis of epic proportions. As these stars exhaust their core helium, instead of gradually expanding into red giants, they undergo a sudden internal rearrangement. Their outer layers contract violently, reheating the stellar surface while the core continues fusing helium in a last-ditch energy surge. But the real trigger might lie in their exotic composition. Blue hook stars often show extreme helium enrichment in their atmospheres, up to 10 times the normal abundance, a trait likely caused by deep mixing processes earlier in their lives. This helium overdose alters how their outer layers respond to temperature changes, essentially creating a thermal feedback loop that reverses their cooling trajectory. Imagine a boiling pot with a lid that suddenly locks tight pressure builds until the system violently resets. That's the kind of thermodynamic upheaval these stars experience in their final act. The plot thickens when we examine their birth conditions. Blue hook stars appear almost exclusively in clusters with high central densities where stellar interactions are frequent. Some researchers propose these stars are actually merged binaries, two stars that collided and combined their material, creating a hybrid object with abnormal fuel reserves and rotation rates. Others suggest they're victims of gravitational pollution, their outer layers stripped by close encounters, exposing hotter interior regions prematurely. What makes them truly invaluable is what they reveal about stellar physics under extreme conditions. Their existence forces us to revise models of how stars burn heavy elements late in life, particularly the complex interplay between convection and nuclear burning in degenerate cores. Some blue hook stars even exhibit bizarre light variations, flickering as pulsation waves ripple through their reheated atmospheres, a behavior seen nowhere else in the universe. As telescopes probe deeper into globular clusters, each new blue hook discovery adds another piece to this thermodynamic puzzle. These stars aren't just cosmic oddities, they're natural laboratories demonstrating how matter behaves when pushed far beyond textbook conditions. And with every observation, we're reminded that even in death, stars can rewrite the rules in spectacular fashion. NGC 6397 isn't like most globular clusters. Instead of a dense, glittering core, its center is eerily hollow, as if something carved out a stellar void at its heart. This gaping absence defies expectations. In a system packed with hundreds of thousands of stars, gravity should pull everything toward the middle, creating a bright, crowded nucleus. Yet here, stars avoid the center like commuters sidestepping a crime scene, their orbits tracing an invisible boundary around empty space, the culprit. A brutal game of gravitational pinball where black holes may have reshaped the cluster from within. For decades, astronomers assumed black holes in globular clusters would be scarce, either ejected by violent encounters or merged into larger beasts. But NGC 6397 tells a different story. Advanced simulations reveal that stellar mass black holes, born from collapsed giant stars, likely sank to the cluster's core over billions of years. There, they didn't just sit quietly. Their immense gravity flung lighter stars outward in chaotic encounters, clearing the center like boulders rolling through a field of pebbles. The result, a dark core dominated by invisible mass where the few remaining stars whiz around at dizzying speeds, their motions betraying the presence of something unseen. The smoking gun came from Hubble's observations of stellar velocities near the void. Stars orbiting the empty region moved far faster than expected, some exceeding 1 million miles per hour, as if gripped by an invisible hand. The math pointed to a hidden ensemble of 20 to 40 stellar mass black holes collectively weighing thousands of suns, their combined gravity sculpting the cluster's strange anatomy. Unlike the solitary black holes found elsewhere, this group behaves like a swarm, their orbits intertwined in a delicate dance that keeps them from merging or being ejected. But the real twist lies in what this means for cluster evolution. NGC 6397 might represent a rare middle-age phase where black holes haven't yet ejected each other through gravitational slingshot. Given time, simulations suggest these dark objects will either merge into an intermediate mass black hole or get flung into the galaxy, leaving behind a more normal-looking cluster. That makes this hollowed-out core a cosmic snapshot, a fleeting stage in a billion-year process that few clusters exhibit so clearly. The implications ripple beyond this single cluster. If black hole swarms can reshape stellar cities so dramatically, they might explain other oddities like ultra-compact dwarf galaxies with suspiciously dark cores. Some researchers even speculate that NGC 6397's void could be a scaled-down version of the mechanisms shaping galactic centers, offering a nearby lab to study how black holes influence their surroundings. Every star avoiding that empty center is a silent witness to forces we're only beginning to map, a reminder that sometimes the universe's most revealing features aren't what's present, but what's conspicuously missing. Globular clusters aren't supposed to defy gravity's math, yet some, like Messier 54, tip the cosmic scales with masses that simply don't add up. This dense stellar city, nestled within the Sagittarius dwarf galaxy, weighs in at nearly 1 million solar masses, far heavier than its visible stars alone could account for. The discrepancy isn't just a rounding error, it's a gaping hole in our understanding of how these ancient structures hold themselves together. The missing mass might be invisible, but its gravitational grip is undeniable, leaving astronomers to wonder, are we seeing the ghostly hand of dark matter or something even stranger? What makes M54 particularly baffling is its location. Most globular clusters orbit galaxies like the Milky Way as independent entities, with gravity dominated by their glittering stellar populations. But M54 sits deep inside a dwarf galaxy, an environment where dark matter should be plentiful. When researchers subtracted the expected contributions from stars, gas, and even the Sagittarius dwarf's own dark matter halo, the cluster still refused to balance. Its stars moved too fast, whipping around as if tethered to an unseen anchor. The most plausible explanation: the cluster itself might harbor a private stash of dark matter, an echo of its formation in the early universe's primordial chaos. This idea appends decades of assumptions. Globular clusters were long considered dark matter deserts, their compact sizes and simple dynamics leaving no room for the mysterious substance. But if M54's excess mass stems from dark matter, it suggests these clusters could be far more diverse in their origins than we imagined. Perhaps some formed within dark matter mini-halos, their stars condensing like pearls around gravitational seeds we can't see. Others might have captured dark matter later, stealing it from host galaxies during close encounters. The plot thickens when we examine other overmassive clusters like Omega Centauri and G1 in Andromeda. Each shows similar gravitational anomalies, yet no two match perfectly. Omega Centauri's excess mass could stem from its suspected past as a devoured dwarf galaxy core, while G1's might trace to a central intermediate mass black hole. This inconsistency hints at multiple pathways to becoming overmassive, some clusters leaning on dark matter, others relying on extreme stellar populations or hidden black holes. The real breakthrough came when astronomers mapped M54's gravitational field in 3D, revealing twisted stellar orbits that no visible mass could produce. Simulations suggest the cluster might be wrapped in a diffused dark matter cocoon, its gravity subtly sculpting star motions over billions of years. If confirmed, this would make it a cosmic chameleon, outwardly resembling a normal globular cluster, but hiding the soul of a dwarf galaxy's heart. Yet alternatives remain. Some theorists propose the missing mass could be legions of faint white dwarfs or neutron stars, their combined heft invisible to telescopes. Others speculate about primordial black holes, dim, ancient objects forged in the Big Bang's first seconds. Each possibility carries staggering implications, whether for dark matter's nature or the universe's hidden populations of compact objects. The deeper we probe, the clearer it becomes. Overmassive clusters like M54 aren't just outliers, they're stress tests for astrophysics itself. Their contradictions force us to question what globular clusters truly are, and how much of the universe's weight slips through our fingers unseen. Every tug of their anomalous gravity is a whisper from the cosmos, reminding us that even the oldest structures still guard their secrets fiercely. Between the blazing stars of globular clusters, there's something else, an eerie, almost imperceptible glow that lingers like cosmic fog. This ghostly light, known as intracluster light, isn't tied to any single star. Instead, it drifts between them, a faint luminescence that only the most sensitive telescopes can detect. But don't let its subtlety fool you. This glow is a relic of violence, a whisper of collisions that tore through these clusters billions of years ago. Take the massive cluster NGC 1399, where Hubble's deep exposures revealed a delicate web of light threading through its core. This isn't just scattered starlight, it's the shredded remains of stars ripped apart during close encounters. When two stars pass too near, their mutual gravity can stretch them into streaming tails of gas and dust, like celestial taffy pulled too far. Over time, these debris fields disperse, their individual particles too dim to spot alone. But collectively, they form a faint backdrop, a sort of stellar graffiti tagging the cluster's violent past. The real surprise came when astronomers measured this glow's composition. Unlike the pristine hydrogen and helium-dominating cluster stars, intracluster light carries traces of heavier elements, carbon, oxygen, even iron, hinting that its origins lie not in gentle evaporation, but in the catastrophic dismantling of fully formed stars. Some of this material might come from red giants, their puffed-up outer layers stripped away during close brushes with neighboring stars. Other contributions could stem from planetary nebulae, their fragile gas shells shattered by gravitational turbulence before they could drift into space. But the most tantalizing clue lies in the distribution of this light. In younger clusters, it tends to cling to the core, tracing recent gravitational upheavals. In ancient ones like Omega Centauri, it spread nearly uniformly, a sign that the glow has had billions of years to diffuse like smoke from a long-extinguished fire. This timeline aligns with simulations showing that clusters experience peak violence early in their lives, when stellar densities are highest and close encounters inevitable. The intracluster light we see today might be the fading echo of a cluster's most chaotic era. What makes this phenomenon so valuable is how it acts as a forensic tool. By mapping the glow's patterns, astronomers can reconstruct collisions that left no other trace. Some clusters show asymmetrical sprays of light, betraying past encounters with rogue star systems or dark matter clumps. Others exhibit radial streaks, evidence of stars being torn apart as they plunge too close to an intermediate mass black hole. Each wisp of light is a clue, a pixel in a larger picture of how these ancient structures evolved through destruction. And then there's the dark matter connection. In a handful of clusters, the intracluster glow appears to warp in ways that can't be explained by visible mass alone. Some researchers speculate this could be the gravitational fingerprint of dark matter substructure, invisible clumps bending the trajectories of free-floating debris. If true, these faint tendrils of light might be more than just stellar ashes. They could be the most direct tracers we have of dark matter's hidden architecture within clusters. The more we study this ghostly glow, the more it blurs the line between creation and destruction. What looks like a silent graveyard of dead stars might actually be a nursery in disguise. Those scattered heavy elements could one day seed new generations of stars or planets, turning the debris of ancient catastrophes into the building blocks of cosmic rebirth. It's a reminder that even in the quietest corners of the universe, nothing is ever truly still. Light lingers, matter transforms, and the past never fully fades away. Globular clusters should be teeming with tiny, dim stars, the cosmic equivalent of a sky filled with countless fireflies. These low-mass red dwarfs, burning their hydrogen at a leisurely pace, were thought to make up the bulk of these ancient stellar cities. Yet when astronomers tallied them up in clusters like NGC 6397, the numbers didn't add up. Where models predicted thousands of faint stars, observations revealed barely hundreds, as if someone had selectively plucked the smallest residents from these celestial neighborhoods. This missing population isn't just a counting error, it hints at a fundamental gap in our understanding of how star formation worked in the early universe. The mystery centers around something called the initial mass function, a cosmic rulebook dictating how many stars form at each size, from heavyweight giants to lightweight dwarfs. In our galactic neighborhood, for every massive star born, there are hundreds of smaller ones, creating a balance that has held true across nearly every star-forming region we've studied. But globular clusters play by different rules. Their stellar demographics skew strangely top-heavy, with an overabundance of Sun-like stars and a glaring deficit of red dwarfs. It's as if the universe cranked up the mass setting during their formation, favoring brighter stars while leaving the smallest ones in short supply. One explanation points to the extreme environments where these clusters were born. The early universe lacked heavy elements, meaning its gas clouds could fragment differently when collapsing into stars. Without metals to cool the gas efficiently, small clumps might have struggled to condense, resulting in fewer low-mass stars overall. Simulations show that in these pristine conditions, turbulence and pressure waves could have prevented the formation of tiny stars entirely, like a cosmic sieve filtering out the smallest particles. But there's a darker twist. Some clusters may have systematically purged their smallest members over time. In the crowded core, where stars jostle like commuters in a packed subway, gravitational encounters favor the survival of heavier stars. Low-mass stars, more easily flung outward by passing behemoths, could have been ejected into intergalactic space over billions of years. The cluster Palomar 5 supports this idea. Its sparse population and stretched-out shape suggest it's hemorrhaging stars, with the lightest ones bleeding away fastest. The real enigma comes from clusters like Messier 12, which not only lack low-mass stars but also show chemical anomalies in those that remain. Some of its smaller stars possess unusually high sodium levels, suggesting they formed from gas polluted by earlier generations' gas that might have been too hot or turbulent to birth typical red dwarfs. This implies that star formation in these environments wasn't a one-time event but a complex, multi-stage process where conditions shifted dramatically between generations. What's at stake isn't just a head count of old stars. If globular clusters defy the standard initial mass function, it challenges our models of how all star clusters, and perhaps even galaxies, assembled in the early universe. Were these anomalies unique to dense primordial environments, or does our understanding of star formation need a complete overhaul? Every missing red dwarf is a silent witness to physics operating under rules we've yet to fully decipher. A reminder that even the universe's oldest neighborhoods still hide startling secrets in their dimmest corners. Terzan 5 isn't just another globular cluster, it's a cosmic imposter masquerading as something far grander. Nestled in the constellation Sagittarius, this dense stellar city shares eerie similarities with the bulging hearts of galaxies, challenging our very definitions of what a star cluster can be. Unlike typical globulars, which host a single, ancient population of stars, Terzan 5 is a layered relic, its stars spanning a staggering range of ages and chemical compositions. Some stars here are as ancient as the universe itself, while others are relative newborns at a mere 2 billion years old. This isn't just unusual, it's unprecedented, mimicking the complex star-forming history of galactic cores rather than the monolithic simplicity of most clusters. The clues lie in Terzan 5's chemistry. While ordinary globulars exhibit uniform metal content, traces of elements heavier than hydrogen and helium, Terzan 5 stars split into distinct factions. One group is metal-poor, typical of primordial clusters, but another is surprisingly rich in iron and other heavy elements, a signature usually reserved for stars born in the chaotic, gas-rich environments of galactic centers. This dichotomy suggests Terzan 5 didn't form in isolation but instead grew episodically, absorbing fresh gas over billions of years to fuel multiple waves of star birth. It's as if this cluster was trying and partially succeeding to become a miniature galaxy. What truly sets Terzan 5 apart is its resemblance to the Milky Way's bulge. Both harbor stars with similar iron-to-hydrogen ratios, and both contain a mix of rapid rotators and sluggish old-timers. Even their spatial distributions align. Terzan 5's core is crammed with metal-rich stars, just like the crowded inner regions of galactic bulges. The parallels are so striking that some astronomers speculate Terzan 5 might be the surviving nucleus of a dwarf galaxy stripped of its outer stars long ago. If true, it would mean we've been misclassifying this object for decades. It's not a cluster at all, but a galactic fossil in disguise. Gravity adds another layer to the mystery. Terzan 5's mass defies explanation based on visible stars alone, hinting at hidden reservoirs of dark matter or a central black hole, features absent in normal globulars but common in galaxies. The cluster's core also hosts an improbable number of pulsars spinning neutron stars that serve as cosmic lighthouses. At least 37 have been detected so far, a density unmatched by any other known cluster. Some of these pulsars are locked in tight orbits with other stars, their precise rhythms distorted by gravitational tugs that betray unseen mass. Could these anomalies be traces of the violent mergers and collisions that shaped Terzan 5's hybrid nature? The most tantalizing possibility is that Terzan 5 represents a missing link in galactic evolution, a glimpse of how the universe's first proto-galaxies might have looked before they grew into spirals like the Milky Way. Its ability to retain gas and form new stars long after its birth suggests that ancient star-forming environments were far more dynamic than we assumed. Other clusters might have started with similar potential, only to have their gas stripped away by galactic tides or supernova winds, leaving them frozen in time. Terzan 5, whether by luck or some hidden stability, held onto enough material to keep writing its story across cosmic epochs, yet the puzzle isn't complete. Why does Terzan 5's youngest stellar population cluster so tightly in its core? How did it avoid being torn apart by the Milky Way's gravity, given its unusual composition? Every answer we uncover raises new questions, blurring the lines between categories we once thought were clear-cut. What's certain is this: Terzan 5 refuses to be pigeonholed. It stands as a reminder that the universe delights in ambiguity, crafting objects that defy our neat classifications and forcing us to rethink the narratives we've woven about cosmic history. Globular clusters harbor cosmic illusionist stars that somehow reverse the aging process, shedding their elderly hues to shine with the vigor of stellar teenagers. These celestial shape-shifters, known as blue stragglers, defy time itself, burning hotter and bluer than any star their age should. Their secret, cosmic theft on a grand scale, where stellar neighbors become unwilling donors in a high-stakes game of gravitational robbery. Picture a binary system in the core of Messier 30, where two stars orbit so closely that the larger one swells into a red giant, its outer layers spilling toward its companion like water overflowing a cosmic bathtub. The smaller star greedily absorbs this stolen gas, piling on mass until nuclear fusion reignites with fresh intensity. The result, a star that should be cooling into retirement suddenly blazes back to life, its surface temperature skyrocketing as it masquerades as a youthful upstart. The original donor, now stripped of its outer envelope, shrinks into a faint, dense remnant, a stellar ghost haunting the system it once dominated. But mass transfer isn't the only path to rejuvenation. In the crowded cores of clusters like 47 Tucani, direct collisions can forge blue stragglers in moments of violent celestial alchemy. When two stars slam together, their combined mass reshuffles the nuclear furnace at their cores, mixing fresh hydrogen into regions where fusion had nearly ceased. The newborn hybrid star emerges hotter and brighter than either progenitor, its chemistry scrambled by the impact like ingredients in a shaken cocktail. Hubble's observations of these stellar Frankenstein's monsters reveal surfaces strewn with peculiar element ratios, abundant helium, depleted carbon, telltale signs of interiors stirred by cosmic violence. The most puzzling cases show no binary companion at all, suggesting some blue stragglers might be triple system survivors. Imagine 3 stars locked in a gravitational dance, their orbits destabilizing until 2 merge while the third gets flung away like a cosmic slingshot. The merged star, now overweight and overenergized, struts across the cluster as a blue interloper, its history written in abnormal rotation rates and bizarre chemical signatures. These lone wolves spin so fast, up to 100 times quicker than the Sun, that their equators bulge outward, distorting their shapes into stellar pancakes. What makes these stars truly invaluable is what they reveal about stellar evolution under extreme conditions. By studying their light, astronomers have uncovered evidence of deep mixing processes that don't occur in isolated stars' currents that dredge up heavy elements from nuclear burning regions and deposit them on the surface. Some blue stragglers even host magnetic fields thousands of times stronger than the Sun's, likely generated by the turbulent dynamics of their formation. These anomalies suggest that in the crowded interiors of globular clusters, stars don't just age, they negotiate their fates through collisions, theft, and rebirth, rewriting the rules of astrophysics one stolen sunbeam at a time. Globular clusters might hold the key to unraveling one of the universe's most electrifying mysteries: fast radio bursts. These bizarre cosmic signals pack the energy of 500 million suns into bursts lasting just milliseconds, flashing across space like celestial strobe lights before vanishing without a trace. While most originate from distant galaxies, astronomers recently detected something startling: a fast radio burst erupting from a globular cluster in the Milky Way's backyard. The implications are staggering. These ancient star cities could be hiding the exotic objects responsible for some of space's most violent outbursts. The prime suspect, magnetous neutron stars with magnetic fields so intense they could strip atoms apart from 1,000 miles away. In clusters like Omega Centauri, where stars are packed shoulder to shoulder, stellar collisions might forge these ultramagnetic monsters. Picture 2 neutron stars spiraling into each other, their merger unleashing a gravitational tsunami that twists their combined magnetic fields into a cosmic dynamo. The newborn magnetar could then unleash sporadic radio bursts as its crust buckles under magnetic strain, sending shockwaves through spacetime. This scenario gained credibility when telescopes traced a fast radio burst to a globular cluster in the galaxy M81, pinpointing its origin near a known X-ray source exactly where a magnetar should lurk. Yet collisions aren't the only possible trigger. Some globular clusters harbor black holes in tight binary systems where a stellar companion feeds them gas. As material spirals inward, it forms a superheated disk that could generate magnetic towers taller than solar systems. If these structures collapse, they might launch focused radio jets powerful enough to be detected across the universe. Then there's the dark horse candidate, action stars. These hypothetical dark matter clumps predicted by quantum theory could decay explosively when nudged by a passing neutron star, an event far more likely in a cluster's crowded core than in the galactic suburbs. The real enigma lies in the burst's irregular patterns. Unlike pulsars, which tick with metronomic precision, fast radio bursts erupt randomly, some silent for years before unleashing multiple bursts in days. This unpredictability meshes with globular clusters' chaotic environments, where close encounters could jostle magnetars like cosmic bumpers, triggering sporadic outbursts. Intriguingly, bursts from the M81 cluster showed downward frequency sweeps, a hallmark of signals plowing through dense magnetized plasma, exactly the soup expected near a cluster's core. What makes this connection so tantalizing is how it ties extreme physics to visible cosmic landmarks. If globular clusters indeed birth these radio phantoms, they'd serve as laboratories for studying phenomena we can't replicate on Earth. Each burst's polarization and dispersion carry encrypted details about the matter it traversed, offering a new way to map the invisible web of gas and magnetic fields threading these clusters. More astonishingly, some models suggest young magnetars might emit gravitational waves during burst ripples that future detectors could catch, giving us a multi-messenger window into these cryptic events. The stakes couldn't be higher. Solving fast radio bursts would crack open mysteries spanning from stellar evolution to the nature of dark matter. And if globular clusters are involved, their role as cosmic time capsules takes on new urgency. Their ancient stars might not just preserve the past, but actively forge the universe's most enigmatic signals. Every millisecond burst could be a distress call from a dying magnetar, or a dark matter grenade's echo, a reminder that even the oldest structures in the cosmos still harbor the capacity for spectacular violence. Beneath the glittering surface of globular clusters lurks an invisible architecture phantom, scaffolding that simulations suggest could reshape our understanding of these cosmic cities. Advanced computer models reveal subtle gravitational fingerprints pointing to dense substructures weaving through clusters like cosmic spider silk, dark matter microhalos, stellar streams from long-dead dwarf galaxies, or perhaps even primordial black hole networks left over from the Big Bang. These hidden filaments don't announce themselves with light, they whisper through the motions of stars, their presence betrayed by anomalies no telescope can directly see. Consider the case of NGC 5139, where stars near the core orbit with inexplicable synchrony, their paths aligning as if guided by unseen rails. Simulations that factor in hypothetical dark matter clumps recreate these patterns with eerie accuracy, suggesting the cluster might be threaded with invisible mass concentrations. Each clump would act like a gravitational tuning fork, orchestrating stellar motions across hundreds of light years. Other clusters show stars mysteriously segregated by age or chemistry along curved bands, arrangements that defy random distribution, pointing to fossil structures from the cluster's violent birth. The most tantalizing hints come from N-body simulations tracking billions of stars over cosmic timescales. When researchers seed virtual clusters with dark matter filaments, echoes of the cosmic web that birthed them, the models produce surviving substructures matching real clusters' quirks. Some show stellar populations partitioned into distinct neighborhoods, separated by invisible walls of gravitational influence. Others reveal spiral-like density waves frozen in time, their patterns preserved like grooves in a celestial record. What makes these phantom structures so revolutionary is their potential to connect globular clusters to the universe's large-scale architecture. If verified, they'd prove these clusters aren't just isolated island universes, but intricately linked to the dark matter skeleton underpinning all galaxies. Every unexplained stellar drift or chemical boundary could be a breadcrumb leading us deeper into the cosmos' hidden blueprint, where visible stars are merely the glitter on a much darker tapestry. Palomar 14 doesn't follow the rules. This globular cluster barrels through the Milky Way's halo on a path so stretched it resembles a cosmic slingshot, its orbit defying every expectation for how such ancient structures should behave. Most globular clusters trace neat, circular paths around our galaxy, their motions orderly and predictable. But Palomar 14 carves a wildly eccentric route, swinging so far out that at its most distant point, it nearly escapes the Milky Way's gravitational grasp entirely before being yanked back in a hairpin turn. This extreme trajectory raises a startling question: how did a cluster so fragile, with stars so loosely bound, survive such a turbulent journey without being torn apart? The clues lie in its velocity. Palomar 14 moves at nearly 1 million miles per hour relative to the galaxy, so fast that by all rights it should have disintegrated eons ago. Typically, clusters with such loose stellar bonds, its stars average 1 light-year apart, couldn't withstand the Milky Way's tidal forces during close passes. Yet here it is, intact. One explanation suggests it wasn't born here at all. It might be an interloper, captured from a dwarf galaxy like the Sagittarius stream, its original home's gravity having shielded it during its youth. The cluster's metal-poor stars support this, their chemical fingerprints matching those of galaxies far smaller and older than the Milky Way. But the real anomaly is its orbit's shape. Simulations show that to achieve such elongation, Palomar 14 must have been flung outward by a cataclysmic event, possibly a close encounter with another cluster or a gravitational kick from the Milky Way's central bar. Some astronomers propose an even wilder scenario. Its path could be the aftermath of a dark matter subhalo's flyby, an invisible structure's gravity twisting the cluster's trajectory like a cosmic boomerang. The stakes are higher than just one rogue cluster. If Palomar 14's survival hints at unseen forces shaping orbits, it could mean our galaxy's halo is far more dynamic and crowded with dark matter clumps than we've assumed. Every deviation in its path whispers secrets about the Milky Way's violent history and the hidden architecture we're only beginning to map. Some cosmic structures refuse to be neatly categorized. They dance along the boundary between two worlds, challenging our definitions with their very existence. Enter ESO 93-08, a celestial oddball that blurs the line between globular cluster and dwarf galaxy, forcing astronomers to confront the possibility that these two classes might be branches of the same cosmic family tree. At first glance, ESO 93-08 resembles a classic globular cluster, a tight-knit sphere of ancient stars orbiting the Milky Way, but peer closer and anomalies emerge. Its stars exhibit a spread of ages and metallicities unheard of in typical globulars, spanning over 5 billion years rather than being locked to a single epoch. More intriguing still is its size, stretching nearly 150 light-years across. It dwarfs most globulars while remaining far more compact than known dwarf galaxies. This Goldilocks scale suggests it might represent a transitional form, caught in the act of evolving from one state to another. The plot thickens when examining its chemistry. Unlike pure globulars where stars share nearly identical compositions, ESO 93-08 hosts distinct stellar populations, some metal-poor like the universe's first stars, others enriched with heavy elements from later generations. This layered history mirrors dwarf galaxies like Fornax, which sustained multiple star-forming episodes as they accumulated gas over time. Yet ESO 93-08 lacks the dark matter halo that typically anchors true galaxies, leaving its identity suspended between two cosmic paradigms. What could explain this hybrid nature? One theory posits it's the remnant core of a dwarf galaxy stripped bare by tidal forces. Imagine a small galaxy venturing too close to the Milky Way eons ago. Its outer stars and dark matter sheared away by gravitational tides, leaving only this dense stellar nugget behind. Supporting this, its orbit traces a path through regions where such violent encounters likely occurred. Alternatively, it might represent a rare case of a globular cluster that somehow retained enough gas to fuel secondary star formation, a process normally quenched in these environments. The implications ripple far beyond classification debates. If objects like ESO 93-08 are indeed missing links, they could rewrite how we understand galaxy formation. Perhaps some globular clusters are failed dwarf galaxies, their growth stunted by early encounters, while certain ultra-compact dwarfs are just overachieving clusters that stole extra gas. This continuum would mean the universe crafts stellar systems along a spectrum rather than rigid categories, with environment playing as crucial a role as initial conditions in determining their fate. Other candidates deepen the mystery. Clusters like Omega Centauri and M54 exhibit similar straddling traits, extended sizes, complex stellar populations, and in some cases trace dark matter signatures. Yet none match ESO 93-08's precise balancing act between the two extremes. Its existence suggests that the boundary between globulars and galaxies isn't a wall but a shifting borderland, where objects can occupy ambiguous states for billions of years. The real revelation lies in what these hybrids imply about cosmic evolution. If dwarf galaxies can be whittled down to cluster-like remnants, and if some clusters harbor galaxy-like complexity, it challenges the notion that size and origin strictly dictate a structure's destiny. Instead, we're seeing a universe that recycles forms, blurring distinctions through collisions, stripping events, and forgotten chapters of star formation. Every hybrid cluster is a palimpsest, a cosmic manuscript where multiple histories are written over each other, waiting for us to decode their layered stories. Globular clusters may seem eternal, these glittering cities of stars persisting unchanged against the cosmic dark, but their fate is far more dynamic than their ancient age suggests. Over timescales that dwarf human history, these dense stellar metropolises are slowly unraveling, their stars scattering into the galactic halo like embers from a dying fire. The process isn't quick or violent, but an inexorable decay governed by gravity's patient hand, transforming these tight-knit communities into wandering nomads adrift in the void. The unraveling begins with gravitational tides. Each time a cluster swings close to its host galaxy's dense core, differential gravity tugs harder on the near side than the far, stretching the cluster like taffy. Stars perched on the outskirts get peeled away, forming shimmering streams that trace the cluster's orbit like celestial breadcrumbs. The cluster Palomar 5 is a textbook example. Nearly half its mass has already been stripped into twin tails stretching 60,000 light-years, a preview of what awaits all globulars given enough time. But tides aren't the only force at work. Inside the cluster itself, a relentless game of gravitational pinball accelerates the dissolution. When two stars pass close, their interaction transfers energy, the lighter star often getting a speed boost that sends it fleeing toward the cluster's edge, while the heavier one sinks toward the core. Over billions of years, this process, known as evaporation, steadily bleeds stars from the cluster like sand trickling through an hourglass. Simulations show that even isolated clusters, those spared close galactic passes, will evaporate through this internal dynamics alone, though the timeline stretches far longer. The end game depends on the cluster's birthplace. Those orbiting giant elliptical galaxies face quicker destruction as they're subjected to stronger tidal forces during frequent galactic mergers. In contrast, clusters drifting in the quiet outskirts of galaxies like the Milky Way may survive for hundreds of billions of years, outliving most stars but still destined to fade. The last stars to depart will be the heaviest, black holes and neutron stars, lingering like ghosts in a crumbling mansion until even they are flung into the darkness. Yet destruction here is also creation. As clusters dissolve, they seed their host galaxies with stellar refugees stars bearing unique chemical signatures forged in the extreme environments of dense clusters. Some may carry planets along for the ride, worlds that somehow survived the chaos. Even more intriguing are the black holes left behind. A single evaporated cluster might scatter dozens of stellar mass black holes across the galactic halo, invisible except for their gravitational influence. Over time, these rogue black holes could merge, forming intermediate mass black holes that sink to galactic centers, perhaps solving the mystery of how supermassive black holes grow so large so quickly. Perhaps the ultimate irony is this: as globular clusters fade, they become part of the galaxy's living structure. Their stars blend into the halo, their black holes lurk unseen in the dark, and their tidal streams weave through the cosmic web like forgotten roads. In dying, they give birth to new possibilities, scattering the raw materials for future star formation, altering the galaxy's chemical evolution, and even influencing where new stars can form through their gravitational wakes. The universe has a way of recycling even its most ancient relics. What we see today as glittering, isolated spheres are transient gatherings, briefly frozen moments in a dance that will eventually scatter their stars across the void. But their legacy persists, written in the motions of galaxies, the distribution of black holes, and the faintest stellar streams that may one day be all that remains of these cosmic elders. Their dissolution isn't an ending, but a transformation, one that ensures their influence will ripple through the galaxy long after their final stars have drifted apart. From stellar vampires stealing mass to hidden black hole swarms, from blue stragglers masquerading as newborns to ghostly dark matter halos, globular clusters have shattered every expectation we've ever had about them. These ancient star cities aren't just relics of the past, they're cosmic laboratories where the laws of physics twist into new shapes. They've shown us stars that shouldn't exist, chemical compositions that defy logic, and gravitational anomalies that hint at entire chapters of the universe we've yet to read. Consider the contradictions we've uncovered. Clusters where stars move faster than gravity allows, yet somehow stay bound together. Places where planets orbit the corpses of dead stars, enduring conditions that should vaporize them, and stellar populations so chemically diverse they look more like galactic collisions than single birth systems. Even their demographics baffle us: missing generations of red giants, inexplicable shortages of small stars, and rogue stars hurtling through space like they've been fired from cosmic cannons. And then there are the questions we still can't answer. Why do some clusters harbor dark matter while others appear completely devoid of it? How did a handful of these structures form so much later than the rest, as if they missed the universe's memo on aging? What truly lurks in their cores? Intermediate mass black holes, pulsar colonies, or something even stranger? With every discovery, globular clusters peel back another layer of mystery, revealing just how little we understand about the extreme environments they harbor. Perhaps the most thrilling realization is this: after centuries of study, these ancient stellar metropolises remain some of the most unpredictable places in the cosmos. They're not just time capsules, they're active participants in the universe's story, shaping galaxies, forging exotic objects, and challenging our definitions of what's possible. So tell us, what do you think hides in these glittering star cities? Could advanced civilizations thrive in their perpetual twilight skies? Might we one day find evidence of physics beyond our current models lurking in their crowded cores? Drop your wildest theories in the comments, because if globular clusters have taught us anything, it's that the universe's strangest secrets often lie where we least expect them. And who knows, the next great cosmic revelation might be waiting in one of these ancient stellar swarms, just beyond the edge of our current understanding. All we have to do is keep looking.